I know what you're thinking. Backwards in time? That's science fiction. That's nonsense. But hold on. Let me show you how we got to this idea, and you can judge for yourself whether it makes sense. This whole thing started with a problem. You see, back in the late 1920s, Paul Dirac wrote down an equation to describe electrons. Beautiful equation. It combined quantum mechanics with special relativity, and it predicted all sorts of things we could measure. The spin of the electron, magnetic properties, everything checked out perfectly. But there was a problem. The equation had two solutions. One solution gave you the electron we know and love with its negative charge and positive energy. But the other solution was bizarre. It described particles with negative energy. Now, what the devil is negative energy? If you've got a particle sitting there with negative energy, and it can go to even more negative energy by radiating, it should just keep radiating forever, going down and down and down. The whole universe should be unstable. Dirac knew this was a problem, so he came up with an idea. He said, maybe all the negative energy states are already filled up. He imagined the vacuum, empty space, as being like a sea, completely full of these negative energy electrons. You can't see them because they're everywhere, uniform. But if you kicked one of these electrons out of the sea, you'd have a hole, and that hole would behave like a particle with positive charge. This was a wild idea, but when Anderson discovered the positron in 1932 in cosmic rays, people said, aha, that's Dirac's hole. A positron is an electron with positive charge instead of negative. Same mass, opposite charge. It's antimatter. But this picture, this Dirac sea idea, it bothered people, including me. It seemed complicated and arbitrary. Why should the vacuum be full of invisible particles? It was ugly. Now, in 1940, I was a graduate student, and I was talking with my advisor, John Wheeler. We were thinking about electrons and how they interact, and Wheeler said something that stuck with me. He said, you know, all electrons are identical. Every electron in the universe is exactly the same as every other electron. Why is that? I said, well, I don't know. That's just how they are. And he said, what if they're all the same electron? I looked at him like he was crazy. What do you mean, the same electron? There are billions and billions of electrons in the universe. He said, well, suppose the electron is like a tremendously long piece of string, and it winds through space and time, going forward, then backward, then forward again. When it's going forward in time, we see it as an electron. When it's going backward in time, we see it as a positron. It's all the same string, the same electron, just moving through time in different directions. Now, this didn't work out exactly as Wheeler thought. There aren't the right number of electrons and positrons in the universe for that simple picture. But the key idea that a positron could be an electron going backward in time, that idea was profound. Let me show you why this makes sense. Suppose you've got an electron moving through space and time. We can draw a picture. Here's space and here's time going upward. The electron moves along, following some path, what we call a world line. Now, suppose at some point this electron suddenly starts going backward in time. What would we see? Well, think about it. An electron going backward in time. What would its charge look like to us? Charge is like a flow. If you reverse time, you reverse the flow. An electron has negative charge. If it goes backward in time, it looks like positive charge is flowing forward in time. That's a positron. Same mass, opposite charge, exactly what we observe. And here's the beautiful thing. When we see pair production, when a high-energy photon suddenly produces an electron and a positron out of nothing, what's really happening? Maybe it's just one electron. The electron was going along in time. Then the photon came along and kicked it, turned it around, and now it's going backward. To us, watching from our perspective, where time only goes forward, we see two particles. The electron continues forward, and what we call a positron, which is really the same electron going backward, appears to be created. And annihilation. When an electron and positron come together and disappear into photons, that's just the point where the electron turns around again. It was going backward. The collision happens, and now it's going forward again. The particle we called a positron disappears because it was never really a separate particle. It was just that section of the path where our electron was traveling into the past. Now you might say, wait a minute, if the electron is going backward in time, shouldn't it know about the future? Shouldn't cause and effect get all mixed up? Good question. But it doesn't work that way. See, when we do the mathematics of quantum mechanics, when we calculate what actually happens, we're always calculating probabilities for what we'll observe in our experiments. And we always observe things in the order where time goes forward. The electron going backward in time doesn't give us information about the future because we're not inside the electron's reference frame. We're observers watching time go forward, and everything we see is consistent with causality. The mathematics, the Feynman diagrams we use to calculate these processes, they work exactly the same way, whether you think of a positron as a hole in a sea of negative energy electrons or as an electron going backward in time. Same mathematics, same predictions, same experimental results. But the backward in time picture is simpler. It doesn't require this infinite sea of unobservable particles filling up the vacuum. Let me show you how powerful this idea is. When we calculate the probability for quantum processes, we have to consider all the different ways something can happen and add them up. Suppose an electron goes from point A to point B. In quantum mechanics, it doesn't just take one path. It takes all possible paths simultaneously. Some paths go forward smoothly, but some paths might involve the electron emitting a photon, and that photon creating an electron-positron pair, and then that positron annihilating with another electron, and so on. Incredibly complicated. But if you think of the positron as an electron going backward in time, these complicated paths become simpler to visualize. You can draw them as diagrams. These are what became known as Feynman diagrams. Though I didn't invent the idea of drawing pictures, I just made them useful for calculations. In these diagrams, time goes upward, and particles moving upward in time are matter. Particles moving downward in time are antimatter. Every vertex where lines meet represents an interaction, and you can calculate the probability for any process by drawing all the diagrams and adding up their contributions. This works for all kinds of antimatter, not just positrons. Every particle has an antiparticle. The antiproton, discovered in 1955, is like a proton going backward in time. The antineutron, same thing. Even particles that are their own antiparticle, like the photon, make sense in this picture. They look the same going forward or backward in time. Now here's something that really bothered people when they first heard this idea, and maybe it bothers you too. If positrons are electrons going backward in time, why don't we see electrons just spontaneously turning around and going backward? Why don't we see electrons disappearing and positrons appearing randomly? The answer is energy conservation. For an electron to turn around in time, something has to happen at that turning point. In pair production, it's a photon with enough energy to account for the mass energy of both the electron and the positron. Really, the electron going both directions from that point. The photon provides the energy to make that turn happen. And in annihilation, when the electron turns around to go forward again, that energy has to go somewhere, into photons. Energy and momentum have to be conserved at every vertex, every turning point. You can't just have an electron in empty space suddenly decide to go backward in time because there's nothing to provide the energy for that turning point, nothing to conserve momentum with. So even though the idea seems wild, it's completely constrained by the normal laws of physics. Let me tell you why I love this way of thinking about antimatter. It takes something that seems mysterious and weird. Antimatter, this stuff that annihilates with matter, and it makes it simple. It's just matter, behaving according to the same rules, but moving through time in a different direction than we're used to thinking about. And it connects to something deep about the nature of time itself. See, the fundamental laws of physics, if you look at them carefully, they don't really distinguish between past and future at the microscopic level. If you took a movie of particles interacting and ran it backward, you couldn't tell. The laws work the same way, so why shouldn't a particle be able to go backward? Of course, there's still the question of why we experience time as flowing in one direction, why we remember the past and not the future, why we see entropy increasing. That's a different question, a bigger question about the universe as a whole and thermodynamics. But at the level of individual particles, the symmetry between forward and backward in time is real, and antimatter is a manifestation of that symmetry. When you do experiments with antimatter, and we can do them now, we can create positrons and antiprotons and even antiatoms in the laboratory, everything confirms this picture. The positron behaves exactly like an electron going backward in time should behave. Same mass, opposite charge, opposite magnetic moment. When it interacts with matter, it annihilates in exactly the way you'd predict if it's an electron running backward along its world line until it meets itself going forward. We can even make detailed predictions. How often should pair production happen? What energies should the particles have? How should they scatter off each other? Every prediction comes out right when you calculate it using this idea of antimatter as matter going backward in time. Now, I should tell you, not everyone likes to think about it this way. Some physicists prefer other interpretations. They say antimatter is just antimatter, a different kind of particle with opposite quantum numbers, and that's that. And that's fine. The mathematics is the same. The predictions are the same. Physics isn't about insisting on one particular way of thinking about things. It's about finding ways of thinking that help you calculate, that help you understand, that help you predict what will happen in experiments. But for me, the backward in time picture is beautiful because it's economical. Instead of saying there are particles and antiparticles, two different kinds of things, we say there are particles and they can move forward or backward in time. One concept instead of two. And whenever you can unify things like that, whenever you can take two seemingly different phenomena and show they're really the same thing viewed differently, you've learned something deep. This idea also teaches us something about how to think in physics. People get very attached to their intuitive notions of how things should work. They say, time only goes forward. Things can't go backward in time. But nature doesn't care about our intuitions. Nature does what it does, and our job is to figure out what that is, even if it violates our everyday experience. The reason we can do physics at all is that we can use mathematics to go beyond our intuitions. We can take an idea that sounds crazy, work out what it would actually predict if it were true, and then check those predictions against experiment. And if the predictions keep coming out right again and again, then maybe the crazy idea isn't so crazy after all. Maybe it's just nature telling us that the universe is stranger and more wonderful than we thought. So antimatter is just matter traveling backwards in time. I know it sounds like magic, like something from a fantasy story, but it's real, it's testable, and it works. Every time we create a positron in an accelerator, every time we observe pair production or annihilation, we're seeing this phenomenon in action. We're seeing a particle turn around in time. And to me, that's one of the most beautiful things about physics. The universe is full of surprises, full of phenomena that challenge our assumptions and expand our understanding. Antimatter seemed like a completely new kind of stuff when it was first predicted, but it turned out to be something even more remarkable, a manifestation of the symmetry of time itself, evidence that particles can dance forward and backward through time, and that what we call creation and annihilation are really just the turnings in that dance. That's the story of antimatter. That's why when someone tells me that positrons are electrons going backward in time, I don't laugh. I nod and smile because it's true. Not true in some metaphorical sense, but true in the sense that it correctly describes what we observe. It simplifies our understanding, and it reveals something profound about how the universe works. And isn't that what physics is all about?